First
Okay,
of all,
thank you,
I am
sir.
grateful to the organizers and Sanjay Agrawalji for having invited me for this talk. And I'll share some of my views on optimization, then particle swarm optimization, then on multi-objective optimization, and lastly, we'll discuss a problem on economic load dispatch and its solution by using the particle swarm optimization methods. So, optimization is the process of finding the best result under certain given conditions. In design, construction, and maintenance of any engineering system, engineers have to take many technological and managerial decisions at several stages. Further, optimization can be defined as the process of finding the conditions that give the maximum or the minimum of a function. You know, we have been trying, mankind has been trying to find out the best possible conditions. That is what exactly optimization means. We have basically two approaches. One is the classical algorithm, other is the stochastical approach, one of which is the particle swarm optimization. In classical algorithms, we generate a single point at each iteration and the sequence of points approach to the optimal solution. Whereas in the particle swarm optimization, we generate a population of points in each iteration, and the best point in the population approaches to the optimal solution. This can be explained again in this form. Let us say we are having a two-dimensional problem. On the horizontal axis, I have shown x1. On the vertical axis, it is x2. We have to start from some points, let us say this point. And if our target point is this one, where I have written target, but this is not known, to us. So we cannot directly move this has changed. Let me do something. Ah, we are here. And let us say this is the target point where we have to reach. But this point is not known. And therefore, the direction from start to end or the target is not known to us. And that is why we go starting from some point, we have to go in some direction which we can estimate. It may be a steepest descent direction, or something else. So we cannot move straight to the target, but we have to move in some way. Let us say it is the way, it's not necessary. And ultimately, we reach this point. But we are starting with a point and we are reaching the optimum point through uh, this path. What happens in the particle swarm optimization? We are having a number of points to start with, and all these points move from one place to other. That means all of the population moves in this way. This is, let us say, first point. That is the second stage, then third stage, and fourth stage. Ultimately, all the points or the whole of the population merges into one point, which we can call as the optimum point. How do we progress in this slide? Yes. The optimization we consider normally is a mathematical process or is a managerial technique, but in fact it is a natural process. That is, we need not to know the mathematics and calculations in order to practice the optimization. Basically, it is a natural process, and that is what I want to stress. If we take an example of plant orientation, we have studied in our early school classes an experiment of placing a plant in a dark room with a window open. And we observed that after a few days, the plant orients itself towards the open window. So the plant itself, which of course is a living being, but definitely does not know the mathematics and definition of optimization, but it tries to maximize the receipt of sun energy. Similarly, we have the theory of survival of the fittest. It says that those species which can adjust their living habits according to the changes in environments can survive, others have to wither away. The examples we can talk about is the dinosaurs and which have withered away. And one beautiful example of something we can call as a dinosaur is the whale, which is not a fish, it's a mammal. And it is believed that it was living on Earth in early times. When there was scarcity of food on the earth, it has gone to water. So whale has adjusted its living habits according to the changes in the environment. So they are trying to minimize the difference between the environmental conditions and their living habits. Next is the businessman. As we know that they want to maximize their profit. Sometimes they may try to maximize their sales, or sometimes in a competitive world, they may try to minimize the sale of the competitor. Then we have the example of housewife who wants to give maximum to the all family members, and within a given budget, she tries to manage all the things plus saving something for the difficult time. When this is an example which is most concerned to all of us, let us say a student is coming to the college and then he has to choose the way of commutation, not nowadays, of course. Then he may be coming to the college for attending the class and he can manage to be late. So he will travel by the cheapest mode of conveyance. But if he is coming to the college for examination, he will have to hire a taxi or cab, and he cannot afford to be late. So it depends on what you want. And move to next slide. But I am finding it difficult to go to next slide. Okay. We give a general statement of an optimization problem. It is to find x is capital here and bold. So it is a vector. It contains various independent variables x1 to xn, which minimizes the function fx. It is a function of several variables subjected to certain inequality constraints represented by G, and it may be any number, say M here we have considered, and we can have the equality constraint of the type represented by H. It may be some number depending on the problem, let us say P. The basic philosophy of most of the numerical methods of optimization is to produce a sequence of improved approximation to the optimum according to certain scheme, which we can say that we start with an initial point, say x1, find a suitable direction of movement, say si, which points in the general direction of minimum, which we hope that it should point towards the direction of minimum, but we cannot be sure about it. Then we find out the appropriate step length, say lambda, for the movements along the direction si, and then we replace the present point xi by another point xi plus 1 by adding to it a quantity where si represents the direction and lambda indicates the magnitude. Then we test whether this xi plus 1 we have obtained is optimum or not. If it is, we can stop the process. Otherwise, we have to repeat. The process. The iterative procedure indicated in the point 4 is valid for constrained as well as unconstrained optimization problems. Now let us start about the concern for today, the particle swarm optimization. And in short, we call it as PSO. It is a robust stochastic optimization technique based on the movement and intelligence of the swarm. It is a simple but powerful search technique and has been applied successfully to a wide variety of search and optimization problems. This PSO applies to concepts of social interaction of the problem solving. You know, you might have come across certain lectures on the personality development. There we say that we should be able to learn from the mistake of ours, and we should be able to learn from the mistake of others. So these are the 2 points which the particle swarm optimization is subscribing to. So we have, it uses a number of agents, that is particles, or we call it a population, that constitute the swarm moving around the search space looking for the best solution. Each particle is treated as a point, or each point is considered as a particle in an n-dimensional space which adjusts its flying according to its own flying experience as well as the flying experience of the other particles. So this particle swarm optimization was first introduced by Eberhard and Kennedy in 1995. So we have the competition with self, that is learning from their own experience. Each particle keeps track of its coordinates in the solution space, which are associated with the best solution. Associated with the best solution or the fitness that has achieved so far by that particle. This value is called the personal best value. of that particle. So the personal best term relates to a particle, but we can have another term that is competition with others. Another best value that is tracked by PSO is the best value obtained so far by any particle in the complete swarm of particles. This value is called the global best. So the term global best relates to the group, whereas the term personal best relates to a particle. So the basic concept of PSO lies in accelerating each particle towards its personal best, G best, P best, and G best, the global best locations, with the random weighted acceleration at each step. So what do you mean by random weighted acceleration? I'll try to explain. Let us say we have a number of points and initially we give them certain velocity of our own. So random velocities. Particles have been selected or created randomly. We have the important terms, the particles, their positions, their velocity. We talk about their personal best, which I have discussed. We talk about the global best of the whole group or the swarm. So these dark dots represent the particles. Arrow represents the velocities, the direction of the velocity, and this light colored indicates the personal best position of the particle, and this dark one, this one, will indicate the global best of the group. So with these terms, we proceed ahead. Each particle tries to modify its velocity and position by using the following information. The information which a particle has got is its current position, its current velocity, and the distance between the current position and its personal best. That means the current position of a particle may not be the best position in its whole life experience. So it knows its current position and it also knows the best position it has acquired so far. Consequently, its current position may also be best, but in general it may not be. Then the distance between the current position and the global best of the group. Then the modification of the particle's velocity can be mathematically found by using the following equation. The equation contains three terms basically. It is, first is the previous velocity it has got. Now we are interested in calculating, finding out the velocity of the particle for future. So we know the velocity of the particle with which it was moving in the previous iteration. Then we know about its personal best position. We know its global best position of the group. We know xi, the current coordinates of the particle. It is xi. So the difference between these 2 points, xp best and xi, is a velocity, is a direction. So this is a term which is corresponding to the experience of the particle history. But it has been multiplied by two factors. One is C1, which is chosen by the programmer, and how to choose we'll discuss. Then because this particle swarm optimization process has no mathematical proof, so whatever we are doing, we may be wrong. And so we have introduced a random factor also. So this factor is generated by a random number generator. Similarly, we have a third term. The explanation is same as to that of the second term, except that we have the term xg best in place of xp best. So in all, what we mean is that we have three velocities. One is its own momentum, that is W into VIK, depending on the previous velocity. Then one is the component which forces the particle to move towards its previously best position occupied. And third factor, or the third velocity, or the third component of the velocity is forcing the particle to move in the best position of the whole group. So these three components combined together will make this the velocity for the particle to move ahead. So these different symbols have been explained here. Then we have three velocities. One is the previous velocity, then a velocity in the direction of the personal best, then we have a velocity in the direction of the global best. So the sum of all these three velocities, that is, one is this, second is corresponding to personal best, and third is corresponding to the global best. The result we call as the next velocity. So once we get the guidance for the next velocity or the velocity of the particle in the next iteration, we are ready to move. So about this W, this is the VIK is the previous velocity, but it should not be given the full weightage. So some less than one weightage is to be given, so that is W. But how do we change W? W, we can expect that initially it can be near to 1, and ultimately it should go on reducing. So it can be, there are various ways of varying W. One thing is that we can keep it as fixed. Other thing is we can change from iteration to iteration. And in general, we can say that this W should go on reducing. And it has been worked out by various researchers that we start with 0.9 and end at 0.4. And then we can calculate the value of W at any iteration by this formula. I is the number of the current iteration, whereas this term maximum iteration need an explanation. While starting the program, we don't know how many iterations the program will take. So we allow the program to run for a certain number of iterations. And we cannot allow the program to run for infinite number of iterations. So this maximum iteration is a number given to us, given by the programmer in the code, which he expects that before that the optimization should be complete. But if it is not completing and it's not getting a solution, the program must stop. So that is maximum number of iterations. So let us talk about the velocity update. We have talked about the three terms. One is the inertia term, second is the cognitive terms, depending on the personal experience, then the social learning term. So in the inertia term, this term forces the particle to move in the same direction as it has been moving before. Second is the cognitive term, and this term forces the particle to move in the local search direction based on its own life experience that we have explained. Third is, again, we have the social learning term. It forces the particle to move in the direction of the best position of the group. That is, this term forces the particle to move to the best previous position of its neighbors. It's a sheep-like tendency, and it becomes a follower. So we have discussed about the value of W, the inertia weight factor. A large inertia weight facilitates a global search, while a small inertia weight facilitates a local search. By linearly decreasing the inertia weight to a relatively large value to a small value through the course of PSO, run gives the best PSO performance compared with the fixed inertia weight settings. So large value of W refers to the global search, small value means the local search. So this is the experience of some people, some researchers, and you may have the different experience. It depends on the problem and the way you are doing it. Then we have to change the position. We have talked about that this is the initial point or the previous point, xik, and we want to find out the next location, that is xik plus 1. K is the number of iteration. Then to which we add the velocity. Now, not only the velocity, we should add some term here as the arrow has been shown. That means the step size. Why it is important? I'll try to explain it through another description after certain slides. So this is the flow chart for the PSO. I have explained it. Now let us say these are some of the interesting slides we can see that initially let us say we have certain number of particles. We have chosen their arbitrary velocities and made them to fly. After we have tried to make them fly, what will happen? We expect that they should come closer, but there is no proof that if they are allowed to move in the arbitrary direction, they may come closer. They may diverge also. So let us say how the particle swarm optimization process proceeds. Initially, we have this layout of certain number of points with the arbitrary directions given to them. After immediately allowing them to move, the situation would be like this. That means they will change their position and the configuration would be different. But now after one move, they've got some idea about their personal experience and the experience of the group. And so after this time, we expect that these particles may come closer and to a better point. So next movement would be like this. That means the area in which the particles are spread out has reduced. And then again, we find that it has further reduced. Next iteration, it will reduce further. And ultimately, the whole of the population will merge into one point. And that is, we have optimized the function. Now, based on what I have presented, we can discuss some points. The behavior of the inertia term W plays a crucial role in the local and global search region. Apart from the points I am presenting here, we can have some other points also, depending on your own experience. The manner in which the inertia weight should be varied during the process of optimization. The cognitive term is important for the local search region, whereas the social term C2 is responsible for the global search region. Now the literature reveals that C1 equal to C2 equal to 2 is an ideal value. But if we want to change that, we want to maintain that C1 is not equal to C2, then in some literature, it has been suggested that the sum should remain as 4. The reason is not known. So we have tried C1 as 1.99, C2 as 2.01. The results were better. But we cannot generalize it. The results were better for particular problems. For other problems, it may not be the case. Now, lower the value of C1 and higher the value of C2 results in the incorrect optimal point and vice versa. Why? The experience reveals that the initial stages of optimization, C2 should be greater than C1. That means we should talk about the global optimization. We should give more weightage to the group rather than in person. For better exploration, exploration means searching for the optimum in the area. And in the final stages of optimization, C1 can be increased for better convergence. So these random factors, they should be considered. This is my own view. You may differ, and in some books it may be different, that these should be considered only when one is encountered with the new types of problems. The new problem means the problem solver does not have any idea about the solution. Once the problem and the nature of the solution is known to the problem solver, these random factors can be safely taken as 1, or means these are not considered. Now, I have to say a few words about the velocity. Let us say velocity is a vector. If we are in a two-dimensional space, we have got two components of the velocity vector, 1 and 0.1. Another velocity may be 2 and 1. In fact, these two velocities are having the same direction. These two velocities have the same direction because if it is divided by 2, this will, if this thing is divided by 2, we will get this one. So both of these two vectors represent the same velocity. It means the direction is same, but the magnitude is different. This means the PSO gives you the velocities with some magnitude associated with them, but this magnitude may not be appropriate, and therefore we need to normalize the velocity vector. This can be done by dividing all the components by a number equal to the maximum number in the velocity vector, and if we do it, it will justify the step size of unity. But then it will add a meaning to the step size. So in this expression for updating the position of the particle, we need some factor here, which we have represented by lambda or k. So finally, we have this expression. But this, all the optimization techniques, we have a point. We want to modify the position of the point by choosing the direction and by choosing the step length. So the different techniques of optimization differ in the way in which the direction of movement is chosen and in the way the step size is chosen. And particle swarm optimization is not an exception to it. We are doing the same strategy for the population size of 20 to 30 is common. Smaller population for optimal smaller population are optimal for PSO from computational point of view. That means if we use the smaller number of particles, the computational effort needed would be less. There is no mathematical proof that PSO is an optimization technique. However, by experience, it has been realized that it is so. So this is an interesting statement about PSO. It's not very clear how PSO converges. This needs more experimentation on the optimization trajectory of the PSO. We can use genetic algorithm along with PSO. We can select, this is one suggestion, it's not from literature. We can select one or more worst points from this swarm and make mating pair with the best points and perform the crossover. So those who know about GA can make out a meaning out of it. Otherwise, if we have, let us say, so many points in the swarm, and let us say this is the worst point and this is the best point. What I mean to say here is we combine these 2 points to generate third point. So it is a combination of the best and worst, and we expect that the optimization process may be getting better by doing so. This is what this statement means. Another alternative is if we select out of say 100 points or 20 points, some 5 points are very bad points, so we can eliminate them and proceed ahead with a better population. So we define another term, that is the constriction factor. That means we are now discussing something, how this lambda, or now we are representing it by Ku, is to be chosen. Now the position update equation has been modified by the inclusion of the parameter Ku, which was lambda in the previous expression, the constriction factor. This we call as the constriction factor, resulting in the following equation. Okay. Then we have another, I'm suggesting oscillation index dt. As the particles cross, this statement we need to read slowly, and I'll explain what does it mean. As the particles cross the optimum point at each iteration and come closer to its subsequent iterations, but do not reach exactly at the optimum solution, this results in a large number of oscillations around the optimal solution. Thus, the basic PSO has also been modified by the inclusion of the new parameter, or say oscillation index. What I mean to explain here is, let us say we are talking about a bird and who is trying to sit here on some projection in a wall, and it is trying to come from the ground level to this point. It will not come directly through this. It will come and stay over this point for a second and then settle down. So this process, which I've experienced, let us say this is the optimum point, that is something which is not numbered, and we are at 1. And we assume that 1 is very close to the target. is not at the target, but we are about to achieve the optimum point. So we start from 1 and go to 2 and bypass this target with a distance like this. Then again from 2 to 3 we move and bypass the optimum point by this distance. This distance is reduced. From 3 to 4 we again bypass the optimum point by a distance. This distance is reduced. From 4 to 5 again the distance is reduced. What actually happens by doing it repeatedly, the distance with which we are bypassing the optimum point would fall down below certain precision value, and then the code will indicate that the optimum has reached. The intention here is that 1 is very close to the target. Then only this happens. And this I have termed as the oscillation. We want to minimize these oscillations or to reduce or to stop it. Then the approach would have been that we know the direction of movement is this, 1 to 2, but we also know that it's not exact direction. So if we move in the normal way, we will reach 2, and then we have to come back. So instead of going to 2, we expect that we reduce the amount of movement and we again work out the direction of movement at, say, let us we call it 2 dash. Then from second point we have to move in the direction this, it is not possible to find out, so we move from 2 to 3 and we make the step size smaller and smaller and reach the optimum point without bypassing it. So that is the basic motivation to construct this constriction factor. So TT user supply parameter for the difference between the values of the variables of the function obtained at alternate iterations. Now D, let us say D denotes the actual difference between the values of the function variables at alternate iterations, that is represented by this expression. So we can put some modifications to the PSO algorithm. Why I'm discussing, it's not a research paper I'm presenting, but you can always discuss what happens in the PSO by proposing certain modifications, posing some problems and all that. So as soon as this difference D is less than the pre-specified value TT, it is observed that the particles come very near to the optimum solution. This results in a decrease in the number of iterations and time by an appreciable amount. Now the position update can be modified by this thing that we have already done. But the only thing is when KU is to be included is indicated by this TT. So we can have the stopping criteria, we cannot allow the code to run indefinitely, we have to stop it. So we have some stopping criteria in all the optimization technique. It may be based on the function values, it may be based on the particle movement, it may be based on the distance between the personal best and global best. All are correct and give good results. But here the intention is to point out that if we use more than one criteria as a stopping criteria, then it will give better results. But it's not free. Using more than one stopping criteria simultaneously may improve the results qualitatively, but at a cost of additional computational effort. So this depends whether we want quality or we want the efficiency. So the initial population is normally taken randomly. If it is done so, the final optimum point achieved may be different every time. It means we achieve only. So if it is that is every time we optimize a problem, we get a different solution. If it is happening, that means we achieve only some local minima, but not the global minima. The reason may be that we have been trying to reduce the computational effort, the efficiency, and therefore the accuracy is suffering. Therefore, the use of multiple stopping criteria may help in achieving the goal optimum. Now we have tried various strategies with RP, RG as these values, CP as 2, and W as linearly decreasing. Then giving different values, W as fixed as 0.6. And again, we have tried to change RP, RG 1, CP, and CG as 1, and so on. But all these strategies work out to be that the best is 4, then second, then 1. It is in the order of merit, and 5th is last. So we can make some more improvements. The particle at the global best value will not move from their present position. However, its velocities will be updated, and this particle will move only when it no more remains the best. Under this situation, the velocity component of this particle would be 0. It means when we have some particle as the global best, we don't allow it to move. We only allow it to move when it loses its designation of global best. So the application of the PSO to the Rosenbrock function, it is a standard mathematical test function, and it is defined by this thing. So we have taken the number of particles 10, it is 2 less. We have taken C1, C2 as 2, and the constants random are 0.4 and 0.5. This can be taken as 1 as well. And we have fixed the tolerance as 10 to the power minus 6. Now, we can generate the random position vectors for 2 variables, say x1 and x2. X1 is a vector, x2 is a vector. Generate the random velocities, say v1 and v2. Number of elements in the vectors is equal to the number of particles in the group. So let me try to explain it. It's interesting to see, because these calculations by hand may take more time. We have started with certain positions of the particles. Initially, let us say this is the position, the middle column, and the random velocities have been given. So the function values, these positions, the function values at these positions are like this. Now we have to define the personal best and the global best. The best value, if the problem is to that of the minimization, then this is the global best. But what about personal best? The particles don't have any experience. They have been just given certain points like this, and the value of the function has been calculated like this. It doesn't have any previous history. So this is the best. So all these positions are the personal best positions, and values of each particle right at the 0th iteration. And of course, the global best can be located. So now we are ready to move. The directions are known to us. So the personal best values of each particle will be their own position in the first iteration. The global best value of the position will be the position of that particle corresponding to which the function value is minimum that I have indicated in the table. And now new velocity vectors can be found out for both the variables by using the previously explained equations, and the new position vectors can be found out. And again, the objective function value is calculated using the new position vectors of the new variables. So at the first iteration, we find that these are the new positions of the particles, and these are the value of the function at these points. We find that the global best has changed from the second position to the 9th position. So this is the global best. Further, we have to identify what about the personal best. Whether for the particle 1, this is the better point or the previous was the better. So in order to compare, let us say put the results of the 0th and the first iteration side by side. The first particle had the function value of say this one, but after this first iteration, the function value has changed and it has improved. Therefore, initially the personal best was these coordinates only, but now, since by moving from this point to this point, it has been possible to find out a better function value. So we should reject this as the personal best, and this should be taken as personal best. So that is the thing. So the same thing is true for first, for second, for third, for fourth. But for the fifth, we find the function value was 143 and now it is 278. So it is not good. So instead of choosing the current position as the personal best, we would like to retain the previous coordinates as the personal best. So that is how it changes. And we have to continue the same thing from iteration to iteration. So you can say at the second iteration, that is the situation. And now we are talking about calculate the difference in the function values for each particle in the current and the previous iteration. We call it delta F. Check if delta F is less than epsilon, the iteration should be stopped. XG best values for x1 and x2 are the required values of variables for minimum values of. Else, if delta F is greater than epsilon, we continue. And finally, in 146th iteration, we find that x1 and x2 assume all particles, assume almost the same value with the suggested modified velocities as 0, 0. That means there is no suggestion for the movement and the final value of the function becomes 0. So now we'll discuss about the economic load dispatch. The economic load dispatch problem is an optimization problem which minimizes the total fuel cost of all the committed plants while meeting the demand and losses. Two aspects of problem M means multi-objective economic load dispatch will consider two objectives. One is to minimize the generation cost, other is to minimize the transmission loss. Then the objective function to minimize the cost of generation is given as the summation of cost of generation for each, and this is the cost characteristic for individual generators. Similarly, we have a function for calculating the losses. But the function to be minimized in a multi-objective scene is this f, which is a functional of fc and fl. How they are to be written is a separate point of discussion. So we'll discuss that also. One is the method of weighting. So we have different weights for FC. FC is the fuel cost of generation and FL is the transmission losses. We put certain weight to it and frame a function F. And it is subjected to an equality constraint, that is demand plus load should be equal to the generation. And inequality constraints is for individual generators, they have got certain minimum and maximum value. In MELD, that is multi-objective economic load dispatch function, it is the relative weights which are more important. That means this WC and WL are important. Therefore, the weight of one of the objectives can be fixed at 1 and other can be varied to see the behavior. And the weight attached to the transmission loss can be varied. Now, this is a point. Of course, it has been made very clear that we want to minimize this function. But simultaneously, we should be able to manage the constraints. There are two constraints. This is the equality constraint, and inequality constraints are managed by PSO of its own, but this is not a part of the function, but it is a part of the problem. So this problem of economic load dispatch is a constraint problem. And what we want to convert this constraint problem into a sequence of unconstrained problems. So we use a transformation, what we call as the Jangle transformation. That is, we put the value of k, we vary k as 1, optimize the problem, then we restart the problem, take it as 10, then as 100 or 1000. Ultimately, we keep k so large so that these things become unimportant. And therefore, the minimum of this capital F and the minimum of this reaches simultaneously. So that is the purpose of Jangle transformation. And I like to explain it through a diagram. That is, if the smaller enclosure indicates the feasible region, that means where all these things are satisfied. So, and we are at outer surface A. By putting k equal to 1, what we are trying to do is we are trying to jump from the outer surface A to B. Then again increasing the value of k, we go to C. That means we reduce the area and come closer to the feasible region. Ultimately, we will fall in this feasible region. So, the optimal power system operation is achieved when various objectives of the power system, that is cost of generation, system transmission losses, and it can be more, that is environmental pollution, etc., are simultaneously attained. But these objectives are conflicting in nature and cannot be handled by conventional single objective optimization techniques. So we define an ideal point. The ideal point is the point where all the objectives attain their minimum values. In upcoming graph, IP shows the point where both Z1 and Z2 objectives are individually minimum. The two objectives now have been represented by Z1 and Z2. It is denoted by Z1 min and Z2 min. So non-inferiority. The concept of optimality is to be replaced by the concept of non-inferiority. What is it? I'll explain through this graph. Let us say we have represent Z1 on the horizontal axis and Z2 on the vertical axis. Now at horizontal line represented by this thing, let us say what is Z2 remains constant and Z1 is minimum value of Z1 is say this one. But at a practical operating condition, we have the point A where Z1 is minimum, but Z2 has got some value. Similarly, at an operating point B, Z2 is minimum, but Z1 has got some value. That means in the expression where we have used the weightage given to Z2 is, the weightage given to Z1 is 1 at A, and weightage given to Z2 is 0. Similarly, we can say at the point B, the weightage given to Z2 is 1, and weightage given to Z1 is 0. But if we have between 0 and 1, we can get a different operating points like A, E, D, F. When we join all these points, we obtain what we call is the non-inferiority curve. Non-inferiority curve. Now all points indicated on the left and below this curve are infeasible, and all points above this curve are feasible. So C is a point where it is feasible. That means constraints are satisfied. But is it a preferable point? Definitely no. So it's not an inferior, non-inferior point. It's an inferior point because we can reduce the value of Z1 from C while moving to A without causing any cost to Z2. Similarly, we can move to point B and reduce the value of Z2 without increasing the value of Z1. So we can have a better point than C. So A is a better point than C, and B is also a better point than C. So C can be improved. So C is an inferior point, whereas we say A and B are both non-inferior points. How? If we try to make a improvement in Z2 by dropping down to this point, we will not be able to reach to this point, but we will reach this point E, where the value of Z1 would be increased. That means while moving from A to C, A to E, we are able to make an improvement in Z2, but at a cost of the deterioration in the value of Z1. So in that way, the AEDFB indicates the set of non-inferior points. So it is known as non-inferiority curve. So that concept would be used, but what we can define is the point IP, where both the functions are minimum, but it is infeasible. What we can do at the most is, we cannot achieve IP. IP is not possible to be achieved. But what we can achieve any point on this curve. But which point should be preferred? The point which is nearest to the ideal point and lies on the non-inferiority curve would be a preferred solution, and that can be termed as, in some sense, the target point. So for locating the target point, we have to work out this non-inferiority curve all through. So let us see. The single objective optimization technique gives the optimal solution in respect of a single aspect. They give the best value of the objective function under consideration. The value of the other objectives at such a solution may be intolerably bad. In such a situation, there is no other solution to facilitate the decision-making process. The way out, therefore, lies in multi-objective approach to the problem. The optimal power system operation is achieved when the various objectives, the power system, cost of generation, system transmission losses, and environmental losses, if it is included, are simultaneously attained. But these objectives are conflicting in nature and cannot be handled by conventional single objective optimization techniques. Inequality constraints, this I have referred earlier also, the inequality constraints have been considered in PSO programming, which is done in MATLAB, and the program checks the power output of each particle at each generator in each iteration, and the power is tied to the corresponding violated limit. Now we fix the value of WC as 1, except in the first row, and weight WL is changed from 100 to 0. So we expect at 1, at this point where the weight to loss is 1, the losses would be minimum. So FL is minimum here, and the cost would be maximum. So let us say about this system. The cost is maximum, loss is minimum, whereas in the other case, when the weightage to loss is 0 and weightage to cost is 1, the cost would be minimum and loss would be maximum. So the same thing is true for other systems also. I am presenting to you the 14 and 30 bus systems also. So the explanation is same, but then we define some more terms. So we need to identify, these are the number of solutions, but what is best out of these? Whether this one is better, or this is better, or this is better. Something in between is better. So is best. So how to identify? It can be observed that the best compromise solution is achieved when the percentage saving of both the objectives is equal, but then we have to define what is percentage saving. So the saving in SFC, saving in FC, the cost of generation. The value of FC when only FL is minimized minus the value of FC when both FC and FL are minimized. We say it is FC max minus FC. Similarly, we define another term, the saving in FL, and we also define the maximum possible saving in cost, maximum possible saving in loss by these terms. And we have reconstructed the table for fiber system in the terms of the saving in cost, percentage saving in cost, and percentage saving in loss. And then we have plotted on the curve the curve like this. And here I may add what is the ideal point. Ideal point is when, is it possible to draw or not? Yes. So this is the point where 100% saving in loss, 100% saving in cost is done. But we will find that this region above the curves indicate the infeasible region. So what is feasible is below these curves and on the left-hand side of this curve. So the point nearest to this ideal point is the target point. But how to locate it? Where the percentage saving is equal. So the one or two slides more. The curve initiates from the point of 100% saving in cost and terminate at the points corresponding to 100% saving in loss. 0% saving in cost and 100% saving in loss is achieved when WL is 1 and WC is 0. When WL is very large compared to WC, as WL is decreased progressively, keeping WC as 1, the percentage saving in FL decreases and the percentage saving in FC increases. Finally, when WL becomes 0, the curve approaches 0, saving in FL and 100% saving in FC. This represents the trade-off between the two. This trade-off word is again need an explanation. Whenever there is a conflict between even between any two people, they may go to police station for their complaints. What police is trying to do, hear both the parties and make a compromise. If there is a conflict, there has to be a compromise. Like K.K. Agrawal, an expert on corona, says, if you get infected with corona, the result would be that you will get healthy. Similarly, when there is a conflict, there is a quarrel, the ultimate thing is that there has to be a compromise. And this is known as trade-off between the two objectives and the cost of generation of the system transmission loss. One would like to operate at IP, that is ideal point, meaning there's 100% saving in both the objectives, but it is not possible. Had it been possible, then means that there is no conflict. Therefore, the attempt should be to operate at a point which is nearest to IP. Such a point lies on the line joining the origin and IP on the curve under consideration. That has been demonstrated on the diagram. So these are certain references, and now I'm open for any discussion and suggestions. I'm not putting the word questions. You can suggest something, you can discuss something. Does the time allow, Sanjay ji?
Yes, sir. Yes, sir. We have time.
So I'd like to get some suggestions from the participants. Should I stop presenting now?
Yes, sir. You can stop your presentation. But dear participant, you can ask question to sir.
It's not question, you can
Yours
give
can.
some suggestions.
You can post in your chat box. I will dictate to sir.
Okay, chat box I can open.
Yes, sir.
Okay, you can write. Udit Mittal says that excellent lecture by Jain sir. Thank you very much for the comments. I'm waiting
Hello,
for the
sir.
question. Yes, you can ask.
Hello, sir. My name is Lokesh from REC Ambedkar Nagar.
Yes,
Sir, I have a question. Uh,
yes.
I am working on optimal allocation and sizing of DG.
Okay.
So, what should we prefer the objectives?
That you have to search yourself.
Sir, I have searched in literature and I
Once
have
you
found.
have identified the objectives, I can go ahead with you how to proceed with it.
Sir, I have objectives like installation cost, carbon emission, real power loss, inverter cost, social welfare, and profit maximization, etc.
Okay. Can you have one objective and solve the problem?
Yes, sir. Real power loss.
You can have another objective and solve the problem.
No, sir.
Real power loss is to be minimized.
You know,
Real power loss.
what I am
I have.
suggest, what I
Yes,
am
sir.
suggesting is you can have if you can solve your problem with one objective, it's okay. But
Okay.
would it be possible to solve with the another objective? Yes, that is also okay. But can you solve with both the objectives? And if it is more than two objectives, tomorrow, Madam Umanangi, I will present to you in three objectives. Now, if there are more
Mhm.
than three objectives, what to do? You have to work out. You can do it. But there are different
Okay,
techniques to not express it on the graph.
sir. I have facing one more problem in selecting
Uh,
weights. If I have more than three objectives,
if you have got more than three objectives, then
then how do I select weights?
how do you select weight? Okay, that I can answer. I think I can try to answer. But then I have to start present also. How can I start presenting?
Just show your screen.
So share your screen.
I have to share, na?
Yes,
You
yes.
have to share your screen.
शेयर कहाँ से करना होगा तो यहाँ नहीं आ रहा वो हमने गूगल मीट पे ज्यादा काम किए हैं ये है ठीक है स्क्रीन है शेयर स्क्रीन आ गया ओके
Yes, sir.
Your screen is
then
visible now.
I have to remove this thing I have to end show then I create a new slide okay now I have got certain function I've got some function say is equal to f1 I hope you mean this thing how to
Yes,
select
sir.
weights
Yes, sir.
okay
ये कहो कि F1 को W1 वेट से
you know
मल्टीप्लाई करेंगे
this mathematics and PSO does not bother about what do you mean by F1, what do you mean by F2, whether it is loss or it is gain or it is
Yes.
money or something.
Okay, okay, sir.
What mathematics or arithmetic is recognizing is what is the magnitude of F1, what is the magnitude of F2, what is the magnitude of F3, and what is the magnitude of F4. Okay.
Okay, sir.
Now there are are some weights to be attached. Say W1. Okay.
Okay.
And then we have some W2. Similarly, we have W3. And your question is find out this W1, W2, W3, and W4. Okay. Am I clear?
Yes, sir. Yes, sir.
Now
Clear.
there is a thumb rule. For maximization, you can write down also, or I should write down, you can take a picture. For maximization, problem, more is more important. Okay. That means if F1 is having the maximum magnitude, W1 should be maximum. So their
Okay.
W1, W2, W3, W4 should be in the direct proportion of the expected magnitude of F1, F2, F3, and F4.
Okay.
For minimization, it would be the reverse. But then
Okay, sir.
not the exact value of W1, W2, W3, etc.
Hello.
You can, but
हाँ.
you can get,
Yes.
you have some idea.
अभी आपको 15 मिनट बाद कॉल करते हैं.
Have I made something clear to you?
Yes, sir. Clear. But how do we select the values for W1, W2, W3?
No, for that you have to work out. You have to
Sir.
find, but I've given you some idea. The relative
Yes, sir. I have
values
got.
W2, W3, W4.
I have got your point. How do we distribute the W1, W2 with respect to the objective function?
I may suggest you may normalize F1, F2, F3, F4 so that ultimately they have got all equal values. So all W1, W3, W4 can be equal to 1. But
Okay,
then
so
how
we are
to
doing.
F2, F3, F4 because we do not have their values unless we have solved the problem. Therefore, it will remain as a dynamic problem. So this normalization formula will also go on changing from iteration to iteration.
Okay.
So I am not only happy if I have solved your problem and if you are satisfied, but if I'm able to confuse you, I am happy. Are you getting my point?
Yes, sir. Yes, sir.
If you can start thinking in the direction I am talking about, I am happy.
Yes,
Well,
sir.
you will definitely get, not now, but after some time.
Okay, sir.
So anything else?
Okay, sir. Thank you, sir.
Any participant, any other participant want to ask question? I think, sir, nobody else wants to ask question to you, sir.
So can I leave?
Thank you very much, sir, for sharing your knowledge and experience with us in such a short notice. You have prepared all the things. Very nice lecture, sir. Thank you very much, sir. Thank you.
Thank you very
You
much.
may end, sir.
Are you recording the lectures?
Yes, sir. I am recording this session.
So
I will mail
can
you.
send?
I will mail you, and
Okay.
we also post this lecture in YouTube.
Oh, YouTube, how to locate?
I will share the link to you.
Okay. Okay, that's good. So I'm leaving.
Yeah.
Thank you, sir.
Thank you, sir.
Welcome.